Check one, check two. Hey, what's up, my chemistry people? Who is ready for a free response practice? A sample of ore containing the mineral tellurite, TeO2, was dissolved in acid. The resulting solution was then reacted with a solution of potassium dichromate to form telluric acid, H2TeO4. The unbalanced chemical equation for the reaction is given below. Boom! Part A. Identify the species that is being oxidized in the reaction. Let's do this. Oxygen will have an oxidation state of -2. Tellurium will then have an oxidation state of +4. Jump over to the dichromate ion. Oxygen again will have an oxidation number of -2, giving chromium an oxidation state of +6. Hydrogen ion, easy enough. +1. Alright, let's jump over to telluric acid. Hydrogen is going to have an oxidation number of +1, oxygen -2, giving tellurium an oxidation state of +6 in telluric acid. Chromium ion, easy enough. +3. Water, hydrogen's got +1, oxygen's got -2. Alright, let's identify the species that is being oxidized in the reaction. As I scan my oxidation numbers, notice that tellurium has an oxidation number of +4 on the reactant side and +6 on the product side. In order for the oxidation state to get more positive, tellurium must have lost electrons. Remember our good friend Leo and what he says. Losing electrons is the process of oxidation. So as we identify the species that is being oxidized, we can identify tellurite, TeO2, as the species that is being oxidized. Now, you could also identify the tellurium 4+ ion as the species that is being oxidized. But it's important to note that you could not say Te, tellurium. This would indicate that tellurium is originally got an oxidation state of 0. So be cautious. Moving on to part B. Give the oxidation number of chromium in the dichromate ion. Easy enough, +6. So pretty straightforward here. Just identify and give the oxidation number. There's no need to write paragraphs or full-on sentences here when you're asked questions like this. Save yourself time, answer the question as indicated, and move on. Let's do part C. It says, balance the chemical equation given above by writing the correct lowest whole number coefficients on the dotted lines. We've got a redox reaction in acidic, boom, solution. So first thing we're gonna do is split this reaction into its two half reactions. We've already identified that it's the tellurite that's being oxidized to form telluric acid. First thing we wanna do is balance for mass, leaving hydrogen and oxygen for last. Tellurium, already balanced. To balance oxygen, we add water. I'm gonna add 2 waters so that my total number of oxygen on the reactant side equal the total number of oxygen on the product side. To balance hydrogen, because we're in acidic solution, we're going to add hydrogen ions. I've got 4 hydrogen on the reactant side, so I need to add 2 hydrogen ion for a total of 4 to the product side. Alright, so our oxidation half reaction is balanced for mass. Now to balance for charge. As I take a look at the things on the left-hand side, they're both neutrally charged. So the total charge on the reactant side here of the oxidation half reaction is 0. On the product side though, although the telluric acid has a neutral charge, I've got these 2 positive hydrogen ions. To balance out the charge, so that the charge on the left-hand side equals the charge on the right-hand side, I'm going to add 2 negative electrons. Now, when you are balancing the oxidation half reaction for charge, you should end up with those electrons on the right-hand side because oxidation losing electrons. Okay, oxidation is half the battle. Let's do reduction half reaction. Notice that it's our chromium in the dichromate that's going from the +6 to the +3 oxidation state. So our reduction half reaction, dichromate ion forming chromium ion. First thing we're gonna do is balance for mass. Save oxygen, hydrogen for last. To balance my chromium, I'm gonna add a 2 in front of that chromium 3 ion. To balance my oxygen, I'm gonna add 7 waters. To balance my hydrogen, I'm gonna add 14 hydrogen ions. Again, we're doing this because we're in acidic solution. So there's a bunch of free-floating hydrogen ions just ready to help us balance this out. Finally, let's balance for charge. On the reactant side, I've got 14 positive hydrogen, -2 coming from that dichromate ion. So my total charge over here is +12. On the product side, I've got 2 chromium ions and 7 neutral waters. So on the product side, my total charge is plus 6. In order to balance the charge, I'm going to add 6 electrons to the reactant side. And again, when you're balancing the reduction half reaction, you're going to be wanting to add those electrons to the reactant side, gaining electrons. All right, so now we have written and balanced our 2 half reactions for this overall reaction provided. Our next step is to ensure that we're losing as many electrons as we're gaining. Our reduction half reaction shows us gaining 6, but our oxidation half reaction shows us losing 2. So we're going to multiply this whole equation by a factor of 3 to get us to 6 H2O, 3 TeO2, forming 3 H2TeO4 plus 6 H plus 6 electrons. Boom! So notice now we are losing the same number of electrons that we are gaining. Our final step is to recombine these 2 half reactions into one complete overall reaction. As I recombine, I'm going to rewrite them as I see them in this overall equation. So I got 3 TeO2 plus just 1 dichromate ion plus, now be careful here with our hydrogen ions, we've got 14 hydrogen ion on the reactant side, 6 on the product side. Those will cancel out and leave me with 8 hydrogen ions on the reactant side, forming 3 H2TeO4 plus 2 Cr3 plus. Be careful with your waters here. 6 on the reactant side, 7 on the product side. So after canceling, I'm going to be left with just 1 water. So my coefficients, 3, 1, ocho, 3, 2, 1. Blast off. All right, as we keep this party rolling, in the procedure described above, 46.00 mils of 0.03109 molar potassium dichromate was added to the ore sample after it was dissolved in acid. When the chemical reaction had progressed as completely as possible, the amount of unreacted excess dichromate ion was determined by titrating the solution with 0.110 molar iron 2 nitrate. The reaction that occurred during the titration is represented by the following balanced equation. Boom! A volume of 9.85 mils of 0.110 molar iron 2 nitrate was required to reach the equivalence point. Calculate the number of moles of excess Cr2O7 that was titrated. Alright, if you're as confused as I am about this problem, I always try to think to myself, how can I get to number of moles? Is there anything that I can use to get to number of moles of anything in this problem? Because generally, if you don't know what to do, it's a pretty good step. I'm going to take my 9.85 mils of 0.110 molar iron 2 nitrate to determine moles of iron 2 nitrate that was required to reach the equivalence point. I can do that using my molarity equation. I know the molarity and I know my volume. A quick jump to my calculator and I'll solve for number of moles. 0.110 times 0.00985. I end up with 0.00108 moles iron 2 nitrate. Now we're trying to get moles of excess dichromate ion. The relationship between iron 2 and dichromate is 6 to 1. So as I set this up, it's going to be 0.00108 moles iron 2. What? Wait a minute. I thought we solved for moles of iron 2 nitrate. How is that also moles of iron 2? For every one of these iron 2 nitrates, there's 1 iron 2 ion. So if I know moles of iron 2 nitrate, I also know moles of iron 2 plus. Quick stoic conversion with a 1 to 6 relationship. I end up with 1.81 times 10 to the minus 4 moles Cr2O7 2 minus. Boom! Science. Part D. Calculate the number of moles of dichromate ion that reacted with the tellurite. Alright, so if you recall, we added 46 milliliters of 0.03109 molar potassium dichromate. But we added so much, we had a bunch of excess dichromate ion. We reacted with that excess dichromate ion with iron 2 nitrate and determined the number of moles of excess dichromate ion there were. To figure out the amount of dichromate ion that reacted with the tellurite, we need to figure out how much total dichromate ion we added and subtract the number of excess moles of dichromate ion. So I am once again going to use my molarity equation. The concentration of my dichromate ion is the same as the concentration of my potassium dichromate because the ratio of dichromate ion to potassium dichromate is 1:1. So 0.03109 molar is equal to X over 0.04600 liters. Calculator! 0.03109 times 0.04600. That gives me 1.43 times 10 to the minus 3 moles dichromate ion total. But remember, we added so much, there was 1.81 times 10 to the minus 4 moles of dichromate in excess. So I'm going to take my total amount of dichromate and subtract the excess amount of dichromate. Calculator. Minus 1.81 minus 4, which gives me 1.25 times 10 to the minus 3 moles of dichromate ion that reacted with the tellurite. Boom, like a boss. That was actually part E, which brings us to our final part, part F for fantastic. It says, calculate the mass in grams of tellurite that was in the ore sample. As we look back at the previous part, it took 1.25 times 10 to the minus 3 moles of dichromate to completely react with all of the tellurite. As I go way back now and think about my balanced chemical equation from part C, for every 1 mole of dichromate, there are 3 moles of tellurite. So let's stoich it up, 3:1. We're looking for the mass in grams. This is coming from my periodic table, and then it's calculator time. Times 3, enter, times 159.6, enter, which gets me to 0.598 grams of tellurite in my sample. Boom!